Thanks for coming to our talk this evening. We've got the lovely Dirk Trauner with us tonight. I'm just gonna give a quick introduction and then give out to him. So, Dirk Trauner was born and raised in Linz, Austria, studied biology and chemistry at the University of Vienna, and received his master's degree in chemistry from the Free University Berlin. He then pursued a PhD in chemistry under the direction of Professor Johann Molzer, with whom he moved to the University of Frankfurt and then back to Vienna. Subsequently, he became a postdoctoral fellow with Professor Samuel J. Danishevsky at the Memorial Sloan Kettering Cancer Center. After 2 years in New York City, Dr. Trauner joined the Department of Chemistry at the University of California, Berkeley, where he rose through the ranks to become an associate professor of chemistry and a member of the Lawrence Berkeley National Laboratory. In the summer of 2008, he moved to the University of Munich, where he served as a professor of chemical biology and chemical genetics. In March of 2017, he returned to the US to become the Janice Cutler Chair of Chemistry at New York University. In the summer of 2020, he became a Penn Integrates Knowledge Professor at the University of Pennsylvania, with an appointment in the Perelman School of Medicine and in the Department of Chemistry. He's a member of the Leopoldina Academy of Sciences and the Austrian Academia of Sciences, and a recipient of the Otto Bayer Award, the Emil Fischer Medal, an ACS Cope Scholar Award, and a Sloan Fellowship. The broad objective of Professor Trauner's research is to demonstrate the awesome power of chemical synthesis and to use it toward the precision control of biological pathways, especially in neuroscience.
Well, thank you so much, Javin, for this lovely introduction. I guess the floor is mine, right? So, can you hear me well?
Yeah, perfectly.
Yes. Great. Okay, good. Great. So thanks for this introduction. Thanks for the invite to speak. I wish I were in London at this time of the year, one of my absolutely favorite cities. And within London, sort of the Bloomsbury St. Pancras area is also one of my favorites. In fact, I would, if I were here, I would probably sip a coffee somewhere on Bedford Square at the Architects Institute. And it's lovely bookstore. But alas, such are the times that we're not free to travel anymore, and therefore I'm thrilled that I can at least meet you online and tell you a little bit about our synthesis, our recent synthesis of tetrodotoxin. I think this is what you were asking me for, and I'd be happy to oblige, because tetrodotoxin is definitely my absolutely favorite molecule, at least at the moment. It's a truly fascinating molecule, which you can see by the fact that you can draw it in so many different ways. This is something I always teach my students when we start with a retrosynthetic analysis of a molecule. Draw the molecule in as many different ways as possible. And you will see that with tetrodotoxin, you really have a lot of views of this molecule that emphasize different aspects. The molecule also is a biosynthetic enigma, which adds, in addition to its structural and architectural beauty, which, by the way, I'm going to elaborate much more in a few minutes, which adds to its attractiveness, is the fact that the true producers of tetrodotoxin are not really known. It's probably some form of cyanobacteria, and many biosynthetic pathways have been proposed. For instance, one that traces back the molecule to a carbohydrate, to epiose, and to arginine as the source of the guanidine, or to isopentenyl pyrophosphate and arginine as the source of these 5 carbons and the rest of the molecule, including the nitrogens. It has been proposed also that the molecule might come from geranyl pyrophosphate and guanidine itself through the intermediacy of this compound here, which lacks the oxa-adamantan core of the molecule. So various biosynthetic proposals have been made, mostly based on the isolation of intermediates. But to this day, the biosynthetic cluster that is responsible, if there is one, by the way, that is responsible for the synthesis of this molecule has not been elucidated. And what further adds to the confusion almost, or the mystery, I should say, the enigma of this molecule, is the fact that it has been isolated from a variety of different molecules, from a diversity of biological backgrounds. Most famously, of course, from the fugu fish. This is the toxin that makes this Japanese delicacy, fugu fish, potentially, or fugu, I should say, potentially toxic. But it has also been isolated from newts. It has been isolated from sea snails, from limulus. It has been isolated famously also from the famously toxic blue-ringed octopus that lives off Australia, and from some amphibia, some frogs, in addition to the newts. So that all points to the fact that the true producers of this molecule are probably some microorganisms that live within these larger organisms, and then these larger organisms are able to accumulate tetrodotoxin without poisoning themselves, which in itself is a fascinating question, how they can do that. It's also an indispensable tool in neuroscience. Every neuroscience laboratory in this world that measures action potentials has tetrodotoxin in an armory, because tetrodotoxin is used to block voltage-gated sodium channels. And this is the source, indeed, of its toxicity. In fact, there's a recent cryo-EM structure that shows how tetrodotoxin is bound to a specific subtype of voltage-gated sodium channels. A little bit more at the end of my talk about this. But if you want to prevent action potentials from firing, you clog the voltage-gated sodium channels, which are all important according to Hodgkins and Huxley, right? Another nod to Great Britain. According to them, you have the successive opening of voltage-gated sodium and then potassium channels, and you can abrogate action potential firing and as such all neuronal activity by blocking voltage-gated sodium channels. And you do this with tetrodotoxin routinely. It's still widely used as an indispensable tool in neuroscience. But as I said, it's also a fascinating molecule from an organic chemist's point of view, and a truly fascinating target for chemical synthesis. And indeed, this challenge has been met several times, actually, most famously initially by Yoshito Kishi, who in 1972 published an absolute landmark synthesis of this molecule. And this molecule was so good that for almost 4 decades, or actually more like 3.5 decades, there was no further work on tetrodotoxin until in the early 2000s, Isobe and then Dubois published asymmetric synthesis of tetrodotoxin with very beautiful chemistry. And this was later on followed by work by Sato and Fukuyama, who, by the way, was the graduate student who worked with Kishi on the original synthesis, and his assistant professor Yokoshima, and so on. There's actually quite a long list of people who have worked on tetrodotoxin, but it has been fully synthesized so far only 6 times before we came along. So why would you want to make this molecule? Well, one thing I forgot to say in my introduction is that tetrodotoxin is actually under development as a drug, yet the natural supply from mostly pufferfish, fugu is a pufferfish, is by no means secure. And in addition to this, we want to demonstrate some advances in chemical synthesis and do this on larger scales than these colleagues have carried out the synthesis before. That's one of the reasons why we were motivated to work on tetrodotoxin. So let's take a look at this molecule now from a synthetic chemist's point of view. First, when you strip it down to the carbon skeleton, you will notice that this molecule has a fairly simple carbon skeleton. It's essentially a cyclohexane derivative with 2 C1 side chains and 1 C2 side chain. Maybe let's go back to the original drawing here. So this is 2 drawings that emphasize the oxaarmatan core, and here's a drawing that emphasizes the 6-membered ring in the middle. It's kind of a roadkill drawing of tetrodotoxin, but I want to use that in order to explain what our radiosynthetic thinking was. So we strip it down to the carbon skeleton. The carbon skeleton is very simple. There are certain structural motifs, however, that make it really interesting. One of them, for instance, is an alpha tertiary amine. This is something that we like to work on, chemical methods to install alpha tertiary amines. Let me actually switch to a laser pointer here. Alpha tertiary amines. In addition to this, you have lots of CO bonds, oxidations, most prominently this oxaadamantane core, while carboxylic acid is bound in the form of an ortho acid with two hydroxy groups. This yields then, in a three-dimensional drawing better seen, the dioxaadamantane core that is so characteristic of tetrodotoxin. And by the way, tetrodotoxin itself is a zwitter ion because this ortho acid is fairly acidic, and of course the guanidine is easily protonated to a guanidinium. So it actually exists as a zwitter ion in aqueous solution. In addition to this, you have further oxidations. Every carbon, in fact, on tetrodotoxin is oxidized with the exception of this one carbon that I'm indicating here. But every other one has a CO bond or a CO double bond. In this case, shown as an aldehyde, which is then tied up in the form of a guanidine, a cyclic guanidine that is in the form of an NO acetal. So that's also a characteristic feature, and for the bioactivity absolutely indispensable is this guanidinium ion in tetrodotoxin. So here it is, the full Monty, so to speak, guanidine and NO acetal present. So from a heterocyclic point of view, however, tetrodotoxin is relatively boring because both the cyclic guanidinium and the dioxaadamantane essentially fall together spontaneously. You don't really have to worry about how they are formed. You can essentially treat tetrodotoxin as if it existed in this open form, where you have a C2 side chain, which is a alpha hydroxylated carboxylic acid, and the guanidine. Once this is there, this will be spontaneously forming the dioxaadamantane core and the cyclic six-membered guanidine by way of an NO acetal. So from a heterocyclic point of view, not a big challenge. These two heterocycles are there, but not a big challenge. However, there are 9 stereocenters. There are 5 six-membered rings. And as I said, it has a densely functionalized central cyclohexane core, which you really have to worry about. And all of the carbons are oxidized by 1. So how did we get into this game? I didn't tell you the entire truth. I really didn't set up to develop an efficient synthesis of tetrodotoxin because I wanted to secure the world supply of this essential and indispensable molecule. I actually did teach tetrodotoxin synthesis as part of a chemical neuroscience course that I have been running in Munich. I had been running in Munich. And while I was teaching this, I came across this paper here by Manfred Kalesse, who used a so-called Kyo-Oka aldol addition to generate this molecule here, shown on the side. Let me actually move this insert here. So what did they do? They started out with this glycolic acid derivative, can be deprotonated and turned into the silyl ketene acetal, which, by the way, you can isolate. So this is actually a really beautiful building block. You can isolate this on scale. And then this building block can undergo a Kyo-Oka aldol addition, where you electrophilically activate an aldehyde with this oxazoborolidine, but not only electrophilically activated towards an aldol type addition, you also then reduce the oxocarbenium ion, which is so formed with that hydride. So you use stoichiometric amounts of this oxazoborolidine. And then the silyl group migrates. So you isolate this this compound. And when you then tickle it with sodium hexamethyl disilazide, you actually move that silyl group over to the hydroxy group here and unmask an aldehyde here. And this looked very tetrodotoxic to me, right? When I looked at this, I thought, okay, I've seen this before. This has features, structural features that are seen in tetrodotoxin, namely these 2 stereocenters here, and then a handle for the further installment of a secondary alcohol, and then a handle to further do something up here. So at this point, I told my group, okay, let's work on tetrodotoxin. And I found a student, fantastic, very talented student, David Conrad, who took it upon him to pioneer the synthesis in our group. So what did David do? First, he added vinyl magnesium chloride, and this actually goes with chelate gram selectivity to diaster selectively install the secondary alcohol here, which was then benzoylated for reasons you will see in a moment. That also matches tetrodotoxin. And then for reasons which I will explain in the next slide, we actually decided not to pursue this further, this opening step, in part because this requires stoichiometric amounts of this oxaza-borolinon. So it's not the most atom economic reaction, although you can recycle, of course, valine and tosyl-valine. But we still decided to use this building block in a different synthesis because it turns out that this motif also occurs in other natural products. So what David did is he first osmolated this double bond here selectively, and then Lindlar reduced the alkyne to the corresponding alkene, and then with per iodate he cleaved this double bond here, or the diol rather, to yield the corresponding aldehyde. And this aldehyde, please bear in mind, because you will see in a moment that it will make this aldehyde on a much larger scale using different chemistry. But the overall building block was there, could still be used, of course, for a synthesis of tetrodotoxin. But David moved on to do something different. First, he added vinyl magnesium chloride, also diaster selectively installing this allylic alcohol, which upon Mitsunobu isomerization, by the way, could use for tetrodotoxin. But our synthesis was diverted then with Grubbs olefin metathesis catalyst. We closed the 6-membered ring. So here is also a 6-membered ring. And then with TRSF, we removed that silyl protecting group, and then we could selectively benzoylate this hydroxy group here, which yielded what is also a natural product known as glycovanol A. Pretty beautiful natural product, and the nifty synthesis. This is a very short synthesis of glycovanol A. It looks like an intermediate with this acetonide here, right? But it turns out that apparently this acetonide is a genuine biosynthetic motif. It's not incurred with some form of acetone chromatography. Apparently, this is truly a natural product, and we made it in this fashion. So back to TTX. We then found that the said aldehyde, this one here, let's maybe go back. This type of aldehyde could be procured on a much larger scale from a chiral starting material. In other words, from a glucopyranoside, from glucose. And in 5 steps, we can convert glucose into this exomethylene tetrahydropyran, which it turns out was also used by Sato in their synthesis of TTX, although in a very different way. We also, when you look into the supporting information of our paper, we also greatly sort of improved the yield and efficiency and the details to get hold of this intermediate. What we are doing now is we are first rolling over that protecting group, that acetonide, what am I saying, the benzylidene protecting group, reductively cleave it in order to install a benzyl group in this position, the secondary alcohol. That actually worked beautifully, gives us a benzyl group on the secondary alcohol and frees the primary alcohol. The primary alcohol was subsequently used for an opening, but before we do this, we actually osmolate this exomethylene group to install the stereocenter of the tertiary alcohol here. So, and of course, the diol that you see in the tetrodotoxin itself. So this matches very nicely onto the tetrodotoxin. These conditions, we can completely diester selectively dihydroxylate this double bond. And then we convert the primary alcohol into primary iodide, but not before we actually protect that acetonide, that diol is an acetonide. Again, with PTSA and dimethoxypropane, we install this cyclic acetal, the acetonide, and we convert the primary alcohol into the iodide under classical Appel conditions. And this is, by the way, also all done in one pot. So you will see a lot of telescoped reactions, as a process chemist would say, in the synthesis where we do several steps in one pot because the reagents are mutually compatible. So we can first protect and then do an Appel reaction to isolate this primary iodide. And now comes one of the first key steps of the synthesis, because this primary iodide is exposed to tertiary butyllithium. Then we squirt in nitromethane, and then we add methyl chloride and triethylamine, all in one operation. So first lithiation, lithium halogen exchange, then addition of nitromethane in the still basic mixture, and then methyl chloride triethylamine. And the outcome is shown here. It's a vinyl nitro compound, an alkene that is formed. And how does this work? This is a Vasella fragmentation, Henry addition, elimination, tandem reaction, where we first promote the iodine lithium exchange to give you the corresponding lithium compound. An isoganate lithium compound undergoes a Grob type fragmentation, which is in this particular context, carbohydrate context, known as the Vasella fragmentation, to yield, to kick out methoxide and to yield the corresponding aldehyde, which is actually the very aldehyde I was talking about before. But to this aldehyde, we add, under these strongly basic conditions, nitromethane, which of course gets deprotonated, makes the nitronate. Nitrate adds in the form of a Henry addition, and it yields initially this alkoxide. Unfortunately, this nitro addition, Henry addition, was not very diastereoselective selective. So we got some selectivities 2 to 1, 3 to 1, 4 to 1 on a good day, but it was never really highly reproducible, this diastereoselective selectivity and satisfying. And therefore, we decided to just add after methyl chloride in order to activate this secondary alcohol, alkoxide, towards E2 elimination, which we promote with additional trifluamine. And that yields then stereoselectively the vinyl nitro compound. But this loss of the hydroxy group, which we need in this position, by the way, was not a problem, because in the next step of the synthesis, we add the alkoxide of para-anesyl alcohol. So we deprotonate para-anesyl alcohol with N-butyl lithium. And then after we warm this to 0 degrees Celsius, we added minus 78 degrees Celsius, warm to 0 degrees Celsius. Then we add after Bock anhydride, bis tertiary-butyl pyrocarbonate, and DMAP, Steglich's catalyst, dimethyl aminopyridine. And the outcome is a molecule that has the 6-membered ring and has all the stereocenters on this ring with correct configuration other than this one, and that one is still lacking. So we are making a bicyclic oxazolene, right? Where the para-anesyl alcohol is incorporated here with the correct configuration when you compare this with tetrodotoxin. So, and here, this C1 side chain, which is tied up in this oxazolene, is mounted in this position, however, with the wrong configuration. So when you imagine that this would become an aldehyde eventually, this stereocenter would be wrong. But since it's next to an aldehyde, we had very strong reasons to believe that this epimerization would be easy and facile. So we marched on with this intermediate, which we could make in this one-pot reaction. How exactly does this work? First, you have a completely diastereoselective addition of lithium alkoxide to the vinyl nitro compound, which can be analyzed in terms of Gram-Felkin-An. I think I have it on the next slide. Yes, and also was analyzed by Nina Strassner and by Ken Hauk computationally. But let's go back first before we discuss this in detail. We have a diastereoselective oxamical addition, and that yields a nitronate. And the nitronate you can electrophilically intercept, for instance, with Bock2O, to make this interesting carbonate. And such a carbonate, which is also a nitronate ester, is very unstable. This very quickly, upon warming, yields or eliminates carbon dioxide and tertiary butanol through this nice cyclic mechanism, which you see here, and a nitryl oxide, which is what we're really aiming for. So we're turning the nitronate into a nitryl oxide. And this nitryl oxide, according to Hüsken, can undergo a 1,3 dipolar cycloaddition to yield the said oxazolidine, which is shown here in 3 dimensions and here in a 2-dimensional fashion. And that, by the way, was completely diastereoselective as well. So both the oxamical addition and the 1,3 dipolar cycloaddition was completely diastereoselective in this key step of the synthesis. This is one, I would say, one of 3 key steps in the synthesis. First really cool one. So here we are, and now we analyze the 1,3 dipolar cycloaddition, the oxamical addition a little bit more. You can create the Gram-Felkin-An model and convince yourself by simple Gram-Felkin-An considerations, assuming that this side chain is the largest one, is R large, in this case, actually beating the benzyl oxy group, that the trajectory is the preferred trajectory, 1 of 6 is the one shown here. And indeed, this was later on in a simplified model system confirmed by Ken Hauk and his student Nina Strasser in calculations that showed that this trajectory, with this being R large, this Bergidanis trajectory effectively in a Gram-Falcon-Ann model is the preferred one to the tune of about 3 kilocalories per mole to yield the correct configuration in this position. The order of events is also interesting because what could happen is that this nitronate, which you intercept with BOC2O, this nitronate ester that is, also undergoes a 1,2-dipolar cycloaddition. This is something that Denmark had investigated. These 1,2-dipolar cycloadditions are also pretty fast, which would yield initially an isoxazolidine with an NO bond, and this NO bond would be rather labile, so a little base would actually give you the product. But it turns out that this pathway has higher activation barriers than the alternative one, where you first have the elimination to the nitrile oxide and then the addition of the nitrile oxide to yield the oxazolidine. Let me quickly turn off my mail program here. All right, so order of events is, according to these calculations, really the one I showed you before. First elimination of the nitrile oxide and then cycloaddition, as opposed to first cycloaddition and then elimination. Important insights that Ken Hauk and Nina Strasser obtained. And here's a 3D version of what I just showed you. So we could confirm the configuration of this key intermediate using X-ray analysis. We could actually at some point also make a crystalline derivative that is a carbamate here. And from this, we could confirm that indeed the stereochemistry was the desired one. The configurations were the desired ones in all positions other than this one, the one that we don't really worry about. Nice crystal structure. I love crystal structures. I always exhort my students to try as many attempts as possible to get crystalline material, because I just like to look at each one of these bonds and look and confirm that the bonds are within the regime that we expect and the angles make sense, and it always does. So how do we now construct the full carbon skeleton? What is missing when you look at this intermediate shown here with the protecting groups all drawn out, which is, by the way, also something I always encourage my students when they run reactions, when they add reactions to the notebooks, please always draw out the protecting groups and all the abbreviations, because you might see some reactivities and some potential byproducts, unwanted byproducts, for instance, that you wouldn't see if you had just the abbreviation PMB and PM. So always draw it out, at least in your notebooks. In a paper, you won't find the space for it, but in your notebooks, you should definitely do this. So how do we add these 2 carbons now? Well, we have an electrophile, not a very good electrophile. We have an oxime ether, a cyclic oxime ether. You can see this oxazoline also as a cyclic oxime ether with a CN double bond. And in principle, you could add a nucleophile to such an imine-like structure, save that this is not a very good nucleophile. And the reason for this is, of course, that this is an allylic anion system, right? That's one of the reasons why oximes are so easily formed, because they are very stable by virtue of resonance structures that correspond to an allylic anion resonance structure. So this has lone pairs here, this oxygen, right? And you can beautifully draw resonance structures that show how this oxygen actually stabilizes this bond. And therefore, we had a hard time to add something here. And in order to make this happen, we first had to actually remove this PMB protecting group and free an alcohol that could guide the nucleophilic addition of an organometallic compound. And the one organometallic compound that worked for us was TMS acetylide, lithium TMS acetylide, which by virtue of this small sp hybridized carbon is a good nucleophile, right? The acetylide anions are great nucleophiles. It's sp hybridized, the anionic, the same reason why cyanide minus is a great nucleophile, because the carbon is sp hybridized, the nitrogen is sp hybridized, it's small and rotationally symmetric. This is what we always turn to when sterical hindrance rears its ugly head. We turn to intermolecularity through coordination and to small nucleophiles. And for good measure, we had to even throw after BF3 etherate to make this really work. And only when we have this witch's brew together, we can actually add these two carbons here. Not with great yield, but we can isolate substantial amounts of the starting material and recover it and resubject it. So overall, we could make still hundreds of milligrams. I think we're on the almost the gram scale still in our synthesis in this at this stage of this alkyne, which bears importantly the alpha tertiary amine. So you have this CN bond that you need in tetrodotoxin, right, with the correct configuration here. And you have all the carbons of tetrodotoxin in place. So all of the carbons are in place. There's a cyclohexane core, C2, C1, C1, right? And 1, 2, 3, 4, 5 of the stereocenters are set correctly, and one incorrectly still. But of course, the wrong configuration, if you will, in this position helped with the addition. That guided the facial selectivity of this addition, in addition to the sort of docking effect or the guiding effect of this alkoxide that you generate in the presence of under these conditions. So you can draw a more sophisticated intermediate with solvents, with THF solvents, but this is a simplified picture of how this alkoxide also helps with guiding a nucleophilic attack, making it intramolecular as opposed to intermolecular. I should actually draw BF3 etherate here as well, because that was needed. So we have now a good amount of this compound in hand. How do we proceed? So what do we actually need to do? We need to convert this alkyne into an alpha hydroxycarboxylic acid. So some form of oxidation has to happen to oxidize both the terminal carbon to the oxidation state of a carboxylic acid and this internal carbon to the oxidation state of a secondary alcohol. Then we need to break this NO bond, right? We need to install the guanidine somehow, and we need to oxidize this primary alcohol to an aldehyde, and then upon deprotection, hopefully everything falls into place. It turns out that at this stage, we were really stuck. We were stuck for like almost a year because many attempts to achieve this ultimately were futile. We could make 500 rings between this hydroxy group here and then even install some hydroxylactones, but the 500 hydroxylactones were unstable, and the configuration of the secondary alcohol was the wrong one in most cases. It was not reproducible. So we actually struggled mightily. And I should mention at this point, a fantastic postdoc, Brian Matsuura, had already joined the effort. And in fact, he was the one who even suggested to do this out of a carbohydrate. Tavi Conrad went all the way to this stage here. So this is where he arrived with the original Kioka approach. And then Brian joined the team, and Brian gave us many more hundreds of milligrams, if not grams, of this intermediate. At some point, David had to graduate. I moved to NYU, and the project was kind of stuck because we had problems with advancing it further, although all the carbons were in place. Until Brian came up with what I think is a really brilliant solution. So first, what Brian did was to reprotect the secondary alcohol as a carbonate. Under these conditions, of course, you also protect the nitrogen as a Bock protected nitrogen. In fact, that was the primary goal, to protect this highly nucleophilic, albeit sterically quite hindered nitrogen as a Bock derivative. Under these conditions, you also incur the Bock group on the secondary alcohol, which is not a problem because that is very easily cleaved, as you will see. And then something happened that really saved our neck. A paper was published that showed that you can debenzylate with DDQ in the presence of light by irradiating it with green light. So it's a photo, I wouldn't say catalytic, a photochemical reaction. It's called chromoselective by Pieber and Seeberger, who published this paper. That this is actually on carbohydrates, to show that benzyl groups can come off under really complex intermediates when you increase the oxidation potential of DDQ with light, by irradiating it with green light. Excited state chemistry, and this was absolutely beautifully. We could get these two benzyl groups beautifully off whilst retaining the alkyne, right? Of course, we could not hydrogenate here. We could not hydrogenate this off. And all attempts to cleave this under nucleophilic conditions or with DDQ itself in the absence of light actually led to ultimate destruction of the molecule. The only conditions that really worked were these conditions published in early 2021. So just when we needed it, when we were stuck again to cleave the two benzyl groups, debenzylate the system and yield this diol. That was a true lifesaver, but such is the nature of total synthesis that sometimes when you're stuck just in a moment when you want to give up, something comes along that allows you to march on. And here is a video that shows how simple this reaction is. We use one of our green LEDs that we also use for our photopharmacology program. You're probably aware that I have a pretty large chemical biology program in my group, where we work with photo switches, with molecular photo switches, and therefore we had all these LEDs, all the requisite LEDs, but the irradiation doesn't have to be very sophisticated. You just irradiate a round bottom flask. Of course, you have Lambert-Beer issues, but since you steer here, this is not a problem. And the overall reaction, which happens still on a half a gram scale at least, actually occurs cleanly. So with that, we could march on, and we could actually deprotect the secondary hydroxy group here, the BOC carbonate, under the simple sampling conditions. So just K-carb and methanol will cleave nucleophilically carbonate. The very mild conditions, under these conditions, of course, the BOC group on nitrogen is retained. And then the the triol can be reprotected, or can be again protected, one of the three hydroxy groups, two of the three hydroxy groups, as a cyclic acetyl, as an acetonide, by treating the system with PTSA and dimethoxypropane, which isolates, and that is the important point, the primary hydroxy group in this position, sorry, the secondary hydroxy group in this position. And now we could investigate 6-membered lactones as opposed to 5-membered lactones, which led nowhere, right? And we could implement what I consider the second key step of the synthesis, a step that was beautifully thought of and executed by Brian Matsuura, by my postdoc, an oxidative hydroxylactonization. But I should mention before we get there, I forgot that, before we get there, we first need to cleave the NO bond here with samarium iodide. Straightforward, works completely cleanly. This is essentially quantitative yield. Then the primary alcohol so formed is protected as the TBS silyl ether. And of course, the BOC group is retained on the nitrogen. So we have an NH-BOC here. And now we have our substrate for the said oxidative hydroxylactonization. We could also have done this before, by the way, but we decided to do it at this stage because there's more flexibility in the 6-member ring. So how does this work? We take this substrate, which in 3 dimensions looks as shown here. So compare again. You have the alpha tertiary amine with the alkyne, with the alkynyl group here, C2 substituent. You have the primary alcohol protected. You have the secondary alcohol isolated here, and you have 2 acetonides. So this is a nice substrate for new chemistry. So we really had to invent a new reaction on the fly by, as always, putting together different pieces that were in the literature. And what Brian came up with was a reaction where we first add catalytic amounts of CP-ruthenium chloride. Then add N-hydroxysuccinimide and sodium bicarb. And then after a while, we add oxone under these conditions, which gives us 71% of the hydroxy lactone with the correct configuration here at the secondary alcohol, the one that matches the tetrodotoxin. And we get a little bit of sort of over-oxidized product, where the secondary alcohol has become a carbonyl, where we get the corresponding ketolactone. So how does this work? A lot of stuff is happening here. I mean, the end result is conversion of these two sp hybridized carbons into an sp2 and an sp3 hybridized carbon with the stereocenter, with the correct diastereoselectivity here, and tying up that primary hydroxy, secondary hydroxy group rather, in the form of this lactone, which of course will ultimately become a part of the dioxaadamantane core of tetrodotoxin. How does this work? So what we think is happening is the following. This is essentially chemistry by McDonald and Trost, the first phase of the synthesis, where we have this CP-ruthenium plus fragment that is known to activate the alkynes. It first coordinates to the alkyne, and then this intermediate here isomerizes to a vinylidene carbene ruthenium complex, a cationic vinylidene carbene. And that was well understood and well known from chemistry that Barry Trost and Frank McDonald had developed before. And that vinylidene carbene can be intercepted by a nucleophile. This is highly electrophilic on this sp hybridized carbon. So we still have one sp hybridized carbon here. Gets intercepted by the secondary alcohol here to form a vinyl ruthenium compound, which is also a dihydrofuran, right? A dihydro, what am I saying? Dihydropuran. A dihydropuran with a vinylic carbon ruthenium bond. And that metal fragment can be protonated off with the help of N-hydroxysuccinimide, can be protonated off. You can make an anionic ruthenium complex now, and this can be protonated off with the protonate, of course, comes from NHS itself. And that then yields, in fact, the dihydropuran. And you can isolate this dihydropuran. It gives actually good yield. You can isolate this dihydropuran and then subject it to various oxidation conditions independently. But what Brian figured out is that there's still ruthenium here, right? This is a catalytic amounts of ruthenium, CP-ruthenium plus or CP-ruthenium chloride. And why not oxidize that to ruthenium tetroxide, which is known to happen when you expose it to oxone, which now gives us ruthenium tetroxide in the same pot. And that can undergo the cycloaddition to this cyclic ruthenate here, which then can break down with known mechanisms to the corresponding ruthenium-4 species. You have ruthenium-8 initially, then you have ruthenium-6, and this can break down to ruthenium-4 and can be hydrolyzed to ruthenium dioxide and our hydroxylactone, cyclic hydroxylactone here. Well, lactones are always cyclic, hydroxylactone here, yielding as a side product, if you will, ruthenium dioxide, which then can be re-oxidized to the ruthenium tetroxide. And this is a new reaction. This is really one of these reactions that we had to invent on the fly. I'm not a methodology-driven chemist, so we're typically target-oriented and not so much methodology-oriented, but it's always nice to sort of invent new methodology when you need it. And I think this is a nice case where this has happened in our work. So here we go. We have now good amounts. We're still in the hundreds of milligrams scales of hydroxylactone, which has everything in place for TTX other than the guanidine. The guanidine is missing here, but of course this can be installed based on this alpha tertiary amine protected. And then the aldehyde, which is masked as an NO acetal, the aldehyde here, which however needs to be inverted in the alpha position for tetrodotoxin to be formed. So how do we do this? First with TMS triflate and lutein, we knock off the Bock group. These are conditions, electrophilic conditions that effectively cleave Bock groups. Under these conditions, of course, you also silate the secondary hydroxy group. And then with TBUF, we actually take off the secondary silyl ether and the primary silyl ether to give us this aminodiol here. And this aminodiol could react with a reagent that was introduced by Yoshito Kishi, one of the best ways to make guanidines out of amines. First, we had to, however, reprotect the two hydroxy groups transiently as silyl ethers, but in the same pot, we added this isothiourea reagent, which in the presence of mercury chloride becomes highly electrophilic and allows us the completion of the guanidine. I always wonder how this really works. It could be that you actually make a carbodiimide, the bespoke carbodiimide, which to the best of my knowledge is actually not stable and not known, that you make this in situ, making a very little hindered sp hybridized carbon again in the middle, which can then be nucleophilically attacked by the amine. So at this stage, we really deal with substantial sterical hindrance, and these conditions, which were so beautifully developed by Yoshito Kishi, they really worked beautifully. And I think everybody else, all the other syntheses of the total toxin, actually using such a step to install the guanidine in this hindered position. So we're almost done. We're getting to the end game. I have to update my slide because this is published since. We are at the end game. So what are we doing at the end game? We need to deprotect, we need to oxidize it and hope that everything falls together under inversion of the configuration here. And this could be done by first oxidizing the primary alcohol silyl protected directly with John's reagent, chromium trioxide, bispyridine, Collins reagent rather, to give us the aldehyde. Under these conditions, the TMS is known to fall off easily, especially from primary alcohols, and oxidation can take place. And that yields an aldehyde masked as an NO-acetal because the N-BOC guanidine is kicking in as a nucleophile and forms a diastereomeric mixture of these two NO-acetals. This is almost the total toxin. What is missing is inversion here and closure of the dioxoadamantane. And that could be achieved by just treating it with TFA in the presence of water, gently heating it to 60 degrees. We get the 70% yield almost over these two steps, both of them, of TTX and of its isomer 4,9, actually not isomer, it's dehydration product 4,9-anhydro TTX, where this secondary alcohol is not tied up in the form of a cyclic tetracyclic, it is NO-acetal. So how does this work? Let's take a closer look at what happens here. A lot of things are happening here, of course. Right? When you think about it, you have to remove this acetonide, you have to remove this acetonide, the TMS has to fall off, this BOC group has to fall off, this BOC group has to fall off, the aldehyde has to be inverted, and then the adamantane core has to be, the dioxoadamantane core has to be formed. So we don't know at which stage what happens. We hypothesize that what happens is the following, that this gets cleaved, this BOC group, or the BOC groups get cleaved first, and then the NO-acetal can eliminate water to make an iminium, or actually if you will, an amidinyl iminium ion. Of course, the positive charge can also sit here, and that can lose a proton, right? And that gives you an enamine-like structure. And the reason why this is favorable is because you leave this A1,3 strain, which you have here. You have a strong synthetane interactions between this oxygen here, which presumably still has the acetal. We don't know that for sure, but you do have an unfavorable steric clash here, which can be lifted through the isomerization, first to the enamine, and then after reprotonation to the isomeric iminium, shown here now with a hydrogen here. I could also put the hydrogen here. That may be actually a little bit easier to follow them. And that iminium here with this amidinyl substituent can either be intercepted intermolecularly to yield TTX, mind that this is aqueous TFA, so there's a lot of water percent, or intramolecularly by this secondary alcohol here to give us the 1 to 1.2 mixture of TTX and anhydrous TTX, which is not the thermodynamic mixture. It turns out that TTX is in equilibrium with anhydrous TTX, which is one of the reasons why we never made an effort to separate the two. By the way, it should be said, of course, at this point we need to be very careful because, as we all know, TTX is a horribly toxic molecule. So there were some safety considerations as well that we had to take into account. But this is not the thermodynamic mixture. And we can indeed reach the thermodynamic mixture by cooking this gently, warming it gently, one should say, 60 degrees Celsius. Under these conditions, these are known conditions, we can reach gradually the thermodynamic ratio between TTX and 4,9 anhydrous TTX here, which is about 2.8 or 2.9 to 1. That's about what you get under thermodynamic conditions. And indeed, we can reach this by equilibrating further. And there is a purification, and recorded some spectra which showed that indeed we had made both. Let's take a good look at the spectra. So in whatever this color is, maroon, you see 4,9 anhydrous TTX. In blue, you see TTX itself. And you can compare, for instance, this position here, which is the one that corresponds to this carbon here, which in the case of TTX has a larger coupling constant. These are anti-periplanar. The two hydrogens have a hydrogen angle of about 180, and therefore you have, according to Kaplus, a larger coupling constant, whereas this one here has a smaller coupling constant. The whole system is also more compressed. And conversely, you can take a look at the NO acetal, which has the similar coupling, of course, the identical coupling constant rather, in both cases, which is similar in chemical shift, but from the coupling constant, you can say which one is which. This again is a sort of 60-degree coupling constant. This is a 180-degree coupling constant that is larger. And then all the other signals were spot on with what was published in the literature. So we do have a nice mixture of the two. When we look at the carbon spectrum, everything is also spot on. This carbon spectrum is actually recorded in a mixture of trifluoroacetic acid, deuteracetic acid, and deuteracetic acid. And I find this quite nice. The residual solvent spectra is kind of a teaching moment because at the level of the CD3 versus CF3 carbon, the sp3 hybridized carbon, you see what you would expect, right? The CD3 is upfilled, and the CF3 is downfilled, and of course has the splitting that you expect from four fluorines, which J is half. So that is all fine, but interestingly, the sp2 hybridized one is inverted. So the CF3, the trifluoroacetic acid carboxylate carbon actually comes upfilled, and the deuterated one comes downfilled, and that is because under these conditions, the CF3 is completely deprotonated, is anionic, whereas the CD3 acetic acid is not deprotonated, and therefore you have this inversion in chemical shift, which I find quite nice. It's always nice to reconfirm things that should be true with actual measurements. All right, let's look at the comparison between TTX in the literature and between our TTX. I don't have to go through this in detail. Suffice it to say that everything is absolutely spot on. So we know we made TTX, and we know that we made anhydrous TTX, because this is also exactly spot on what we expect from the literature. So in summary, what have we done? We have synthesized TTX in 22 steps. Very fast synthesis in comparison with others. Others are between 30 and 40 steps. We could increase the yield or the scale of our synthesis easily to 0.5 gram. We haven't done it, of course, because we did not want to risk the toxicity that is associated with that. But if necessary, if this becomes an issue, I think we could actually scale the synthesis up nicely. It's certainly the shortest and the most efficient synthesis that has been published. It can be traced back to very simple starting materials like glucose, glucopyranose, and nitromethane, dimethacetylene. This is the source of the extra carbon in this position. And then, of course, the guanidylation reagent, none of the carbons of glucose are lost. And 2 of the stereocenters in glucose are actually retained. So this is quite efficient in terms of exploiting the chemistry of glucose. And this was published, again, I should update the slide here because some month ago, this was published in Science. And if you want to read more about the synthesis and revisit some of the steps that I've just discussed, please read this paper, which was a great conclusion for us and made my students very happy. As you see from the somewhat long author list, a lot of people worked on it over the years. And we had also some computational input from the Hauck group from UCLA, but it was absolutely satisfying in the end because we can claim that we have the most efficient and the most scalable TTX synthesis by far, actually. The overall yield, I think, is something in the range of 15%. So where are we going? Before I stop, I want to mention that we now want to use this efficient platform, synthetic platform, to come up with selective blockers of a specific voltage-gated sodium channel, one known as NAV 1.7. Here's the recent cryo-EM structure, 2 years old now, of TTX bound to NAV 1.7. The challenge is not so much to find a derivative of TTX that binds better to NAV 1.7, but the challenge is to find some that do not bind to the other 8 isoforms, because if you block NAV 1.1 or NAV 1.5, you die from respiratory failure or from heart failure, respectively. Yet TTX is, as I said, under development as an analgesic for neuropathic pain, and TTX itself. We think we can do a little bit better by making TTX derivatives that show some selectivity. I want to thank all the students that have participated in this. I mentioned many of them already, actually all of them, in particular Brian Matsura. He's now at Merck in South San Francisco, who carried this over the finish line. I promised him that if he finishes, I'm going to do a dance on Washington Square, impersonating somebody, and now I have to do it. Stay tuned for that. Peter Röhmann, fantastic synthetic chemist, still in my group, scaled up the last steps and actually ran essentially through the entire synthesis one more time to clean it up and to do our revisions, and he was helped by Belinda Hetzler. And the whole thing was pioneered by my student, David Conrad, who is now an assistant professor at the University of Munich and has a fantastic research program by himself, dedicated to neuroscience, but also to cancer. So watch out for papers by David. With that, I would like to thank you one more time for listening to me, and I would be happy to answer questions.
All right, thanks so much for that, Dirk. That was extremely interesting. Does anyone have any questions? If not, I will go ahead with mine. What would you say is like your best takeaway from this? Like, what did you find most interesting? What do you think is going to be the most memorable for you?
Yeah, the most memorable for me was the day when Brian Matsura came into my office with a smirk on his face, which told me that I have to do that dance. Right? So that was a good day. You know, when we did the cycloaddition chemistry, the Huysken cycloaddition chemistry, I cut this out somewhere. I had a slide on here where I wanted to acknowledge not only funding by NSF. Somehow I cut this out when I prepared this talk, but I also wanted to acknowledge my former colleague, Rolf Huysken at the University of Munich. Let me actually see whether I can find this. Let me do this because I wanted to really do this. So I was a colleague of Rolf Huysken, who did not get the Nobel Prize for the logic of one-to-dipole cycloadditions, right? He was the one who really saw what everybody else saw, but thought what nobody else had thought before. Namely, that one-fluid dipolar cyclic addition can be firmly put into the framework of the Wilbert-Hoffmann rules. And this is an older picture of myself with Rolf Hüsken, who passed away 2 years ago, and at the age of 99, almost made it to 100. And Tommy Magauer, who was our assistant professor back then in Munich. And when you think about it, Rolf Hüsken's work, his work on alkyne azide chemistry, his work on one-fluid dipolar cyclic addition chemistry really paved the way for yesterday's Nobel Prize, which of course went beautifully to my former colleague Caroline Bartolsi and to Barry Sharpless again, and Martin Meldau. So we'll shout out for Rolf. His work was absolutely crucial for us to be able to make the toxin.
Thank you so much for that. Very interesting, and we've had someone here say very nice and interesting talk. Thank you.
And have a glass of wine on me, okay?
So is there any other questions? And if not, we're just about coming up to time. So
hopefully I can visit UCL at some point in person. I've actually never spoken at UCL, so I give my regards to your colleagues.
yeah, absolutely. If you're down in London, drop us an email and we'll definitely fit you in.
You can see this as a down payment, and one of these days I will hopefully be able to visit you in person. And good luck with everything, and enjoy the rest of the day.
Yeah, have a lovely rest of your day. Thank you so much.
Bye.
That was really good. Thank you. Yeah, well done. Martina's here as well, if you want to.
I am dead inside. Hi.
Oh shit. No, wait. No, wait.
No, it's fine. It's fine. She's my friend. I'm literally in the same room as her right now.
Okay. Yeah, I will watch the recording because the talk seemed very relevant to my, what I will study this year. In terms of
it was actually it was very chemistry based, very knowledge based, but I'm sure it would be interesting for someone who understands what he was
I was
going
telling Dipali that Dipali will study some of the reactions in this year, in third year. So
yeah,
it was definitely very useful.
Reagents. Oh my gosh.
Yeah.
Wow, well done.
Oh,
That's
amazing.
Good. I was just kind of blanked, honestly. But yeah.
Yeah. No, it was a lot of reactions, but it was useful knowledge, I think. I will watch the recording.
But yeah, well done. That went so well.
Yeah.
Yeah. Okay, have a nice night.
You too.